So we are very happy to have Gavin Brennen today. He's a speaker today, and he's going to tell us about some work has been doing with over a period of time. And I have read, I think, his first paper on this topic, and we have been very interested to follow it up to understand what he has achieved so far. So he'll be telling us about relation of QFT states with wavelets. Over to you, Gavin.
Thanks very much. Pleasure to be speaking here. So, yeah, this work is just been going on for a few years. Started kind of with a motivation of can we take some ideas from signal processing to understand quantum field theory. So just taking kind of a quantum information approach to field theory, where we cope with the fact that we don't have continuous fields that can be described in terms of finite resolvable measurement apparatus, by just admitting the fact that we're only going to be able to talk about our observations of a field at some resolution. And the typical approach taken in condensed matter is, for example, to put things on a lattice. And of course, that's been used in lattice field theory as well, and it's been tremendously successful over many decades. But now that we've developed quantum information theory quite a bit over the past 2.5 or 3 decades, we thought we would try to combine some of the ideas, particularly involving concepts like entanglement, to descriptions of quantum field theory, but doing so with finite resolution description of the degrees of freedom. So that was the basic motivation for this research. And I'll share some of it. It's certainly ongoing, and I'll just hint at some of the things we're looking at the end. But just to get us on a common footing, I'll just start off with a primer on wavelets, because I know everyone is certainly not aware of them, or it's always nice to see a refresher if you are aware of them. And then I'll talk about how the wavelet representation of fields can be described as an exact holographic mapping, so that there's a concrete realization of a bulk boundary correspondence, in the sense that all the degrees of freedom in the bulk of like a 2-dimensional system could be understood in terms of degrees of freedom on the boundary of that system, where the bulk will be described in terms of the parameters that show up in the wavelet modes. And then I'll talk about how this idea could be useful to witness quantum phase transitions by making use of compression that we are using with the wavelet description. And then I'll talk a little bit about how one could, in principle, engineer this kind of bulk boundary correspondence in a laboratory for a simple scalar bosonic field theory. And then I'll just close up with some comments about how this could be applied for quantum algorithms based on wavelet encodings, where we could imagine a future where we have quantum computers that could simulate quantum field theories. Okay, so just to start out with the basics of what wavelets are, they are modes or functions at this point, we can say, that fall into 2 types. There is a father function, also called a scale function, S of x.
Gavin,
and yeah.
Are you changing your slides or not?
Yes. Oh, you can't see it?
No.
Okay, let me Can you see those change?
Yes, now we see a new slide.
But can you see me changing over several slides now?
No.
Okay, then I'll have to do things this way. All right, I'll do things this way.
Okay.
So hopefully that's, I'll have to just watch it like that. I don't know why it's not advancing. Okay. So yeah, we have these two types of functions that appear in wavelet analysis. There is the father function or scale functions, S of x, and the mother functions or wavelet functions, Wx. And these functions are defined with some special properties. So the father function is a solution to a renormalization group equation. That is, you demand that the function is equal to itself when you translate it over some integer number of steps with some weights, and then you apply a dyadic scaling. So it's sort of like, it's a function where if you sample it at different integer translations and then scale that, then you get the same function back. So by dyadic scaling, I mean that it's by a factor of 2. So it's like a coarse grading by a factor of 2. And the translations are integer translations. And the coefficients that show up in the weights on these translations, you can sort of think as the DNA of these father functions. So these are solved for according to some conditions that you want. So these are called the wavelet coefficients, and the choice of them determines the kind of wavelet family you use. And different wavelet families can be useful for different applications. I'm going to focus on a particular wavelet family called the Dabuchet wavelets, named after Ingrid Dabuchet, who invented them in the 80s. And they are have this property that it's a unique minimal ordered set of these wavelet coefficients defined such that the first capital K moments of the mother function vanish. So I'll get to why that's important in just a minute, but just to point out that the mother function, or the wavelet function here, W of x, is related to the father, but with some inversion with some minus signs. So the mother and father is kind of genetically related here. They, as constructed, these functions have some nice orthonormality properties. So you can, starting off with the father function, if you apply a dyadic scaling, you get another father function, which we could call S of k, where the superscript k tells you how many times you've applied this dyadic scaling. And a subscript tells you how many times you shift it. So these father functions are defined so that when you're at the same scale, different integer translations of them are orthogonal. And a similar thing happens for the wavelet functions, but also for the wavelet functions, if you're at different scales, they're orthogonal. And the final property we have is that the wavelets are orthogonal to the scale functions when the scale of the wavelets is greater than the scale of the father functions. So it's better to see a picture to see what these kinds of things look like. So this is a family portrait of the Derbyshire wavelets, just plotted here in the different boxes. We have different father and mother functions for different index capital K. So the orange is the father function. At some base scale, we call it 0, and some base translation, which we also call 0. So in the case for capital K is 1, the father function is just like the top hat function, and the wavelet is the sawtooth. So these are also called Haar wavelets. It's the most basic wavelet, and if you like, you could think of what's used in condensed matter when you just put a field on a lattice is just like using this formulation. So you just kind of average field over some bin, and you say, okay, I describe a mode with support on that region of space. If you go to higher index K, you start to get things which are more jagged, but things start to get smoother as you increase K. And it turns out that the increased K Derbyshire wavelets have more vanishing moments, which makes them better approximations for describing features of a system. So it gives them the property of being more efficient representations of data. If you could kind of think of it as if you have a function and you perform a Taylor series expansion about a point, then the for higher K, you have K minus 2 0 moments. So that's the only information you need to encode as you go to higher K is higher order Taylor series expansions of a function. So in a sense, it gives you a more sparse representation of features of data. So how does this come into play when we think about more general functions? Well, these wavelets give you a countable basis for square integrable functions. So if we look at L2 of R, square integrable functions on the real line, we could think of this as a direct sum over subspaces corresponding to spans over scaling functions and wavelet functions. So in particular, the scale functions, those are the father functions at some base scale 0, and all their integer translations define some vector space H0. And then the wavelet functions at scale 0, these are the ones that are the mother functions. We call those W0. And then if you perform a scaling on those wavelet functions, so you shrink them by a factor of 2 and you increase the amplitude so that they have the same integration. Orthonormality property, we call that W1, and you do another scaling, you get W2, etc. If you go all the way to infinity, this gives you a basis for L2 of R. And in particular, we can view the wavelet functions as providing a refinement for coarse-grained scale function representations. So the vector space of scale functions at some scale R+1 is equal to scale functions at a coarser scale plus some wavelet functions which are a refinement. And sort of a way to keep this in mind is we just pay attention to this K equals 1 family, this Haar family. The scale functions are the top hats, so they kind of perform an averaging over a region of space, whereas the wavelet is this sawtooth kind of function, and it actually computes differences. So you can think of the scale functions as averaging and the wavelets as taking differences. So it sort of provides you a way to perform bandpass. They act as a bandpass filter. So things that, if you were to look at this kind of refinement, finer details can be described as coarser details plus difference degrees of freedom. These wavelet functions give you degrees of freedom associated with differences of a function. And if you just iterate this procedure, then the vector space for scale functions at some scale n can be just written as scale functions at some very coarse scale 0 plus a lot of refinements up to scale n-1. And this is a way to view the holographic principle in a wavelet transform. So here is an example for a system, say in one spatial dimension with periodic boundaries. So the red degrees of freedom here could represent scale degrees of freedom at scale n. And that's described by this vector space H sub n. And the wavelet description says that this vector space is actually equivalent to the vector space H0, which are these very coarse scale degrees of freedom at scale 0, plus all these blue degrees of freedom, which are associated with wavelet modes from scale 0 up to scale n-1. So all the blue dots plus the green dots is the same number of degrees of freedom as all the red dots. And that's why sometimes you'll hear wavelets as sort of adding an extra dimension to your description of data. You have a position index, which in this case tells you how long you're going around the circle, kind of your angular degree as you go around the circle. And then you have a radial index, which tells you about your scale. So coarse scales, very broad features, are described by a small radius, and fine scales are the much larger radius. And I've just illustrated here some patches. So like if you wanted to, because this is an exact mapping, I've listed here like a field phi at scale n and position m can be rewritten in terms of all these degrees of freedom contained in this kind of leg-shaped, lamb chop-shaped shaded figure. And the same thing for another degree of freedom. So if you wanted to look at like correlations between these two, it would involve overlaps between the degrees of freedom illustrated there. Okay, so how can we get some intuition about how these wavelets encode information? Well, here's just a photo of the Sydney skyline. And if you just perform a wavelet transformation of this image data, it's represented in a multi-scale basis here. So the upper left corner contains just the very coarse information about this figure. In fact, it's a highly compressed representation of this figure. And you get refinement by looking at the details which are contained in these other square regions, where as you go further to the bottom and the right, you get increasingly fine detailed descriptions. And you can also see that because of the 2D nature of this information, whether you're on the upper right or the lower left determines whether you're going to get fine information along the x-axis or the y-axis. So like these long vertical stripes contained in this building are captured in the upper right, which is capturing fine detail along the x direction, whereas the kind of horizontal degrees of freedom, the details associated with these buildings are captured in the lower left.
Gavin, can I ask a question?
Sure, yeah.
So do you have something, in this basis, I thought you also had dependent on position and scale both. So you have some directional thing also or not?
Yeah, so like here, if I write these functions, like they have a superscript index which tells you the scale and a subscript which tells you the position. So you have like sort of 2 degrees of freedom, a scale and a position.
Yeah, but in this photograph you showed us, you were talking about direction and scale, not position and scale.
Yeah. So yeah, just because this is a 2D figure, you can see that you can capture either fine degrees of freedom along the x-axis or fine degrees of freedom on the y-axis, depending on whether you're on the
Okay.
lower left or upper right of this wavelet transform.
Okay. I see.
Yeah. Okay, and I mentioned this defining characteristic of these Derbyshire wavelets is what's called the index, capital K. And we saw that larger capital K gave us scale and wavelet functions which looked smoother. And in particular, larger K means you have more vanishing moments, which, as I was saying, results in a sparser representation of data and giving you reduced error. So this is just an illustration of this, where I look at this top compressed upper left corner of the figure, but I do it for different values of capital K. So things look smoother as you increase capital K. You're getting a more information out. There is a cost to pay, though, because if you use larger K, the computation involved with performing the wavelet transform increases, although it's a modest increase. Okay, so let's go ahead and apply this to some free field theories. So we looked at a couple. The first was the free Ising model using the Majorana spinner formulation. So this is the field theory you get out when you take like the 2D classical Ising model and ferromagnetic, and then you look at the corresponding quantum Hamiltonian, which generates the transfer matrix for that 2D Ising model. And this can be written in terms of Majorana field modes, so these are field operators B, which depend on space X, and they also carry a spin label sigma, which can be 0 or 1. So this is a Majorana spinner, and the components satisfy the anti-commutation relations for Majorana operators. So these are self-conjugate operators. And the characteristic parameter for this Ising model, so here I've written down the Hamiltonian density, is the mass M0. There's a derivative term and a mass term, kinetic energy and a mass. And so there's 2 characteristic phases for this model. In the massless phase, the correlator between 2 of these Majorana field components satisfies this condition. Here I've imposed anti-periodic boundary conditions on a system of size capital X. So this correlator exhibits algebraic decay of correlations as a function of the separation between the Majorana modes. And so we can write down this Hamiltonian in a wavelet basis by defining wavelet mode operators in the Majoranas. So you just take your Majorana spinor component, which is a function of space, and take the overlap with some scale field at position L and scale 0. And that'll define a Majorana mode at scale 0 and position L. And these positions take values in the integers on a lattice. And then this is a quadratic model, so we just have some matrix which defines the interactions. Oh yeah, sure.
Is it obvious that the Hamiltonian is local in the scale?
So what I've done here is I've simply rewritten the continuum fields at a particular scale. So this is a Hamiltonian at a particular scale. You can so in other words, it's very similar to just a lattice treatment for a field theory, where I'm choosing my modes to be scale modes at some scale 0. I could rewrite this. And I'm going to do this, and I'll show this in a few moments. I can rewrite this in a multi-scale basis, where now we'll have an index both for wavelets with some scale index and position index. But here I'm just writing it in terms of the scale fields. So if you like, back when we look at this holographic principle, I'm just looking at the left-hand side of this equation here. So I'm representing the field just using the scale modes, which are always at a fixed scale. So it's sort of like I'm looking at the treatment as if it was a boundary theory with just the scale modes. Does that answer your question?
Yes, maybe I'll ask again later.
Yeah, sure. Yeah. And also notably, the derivative overlap coefficients can be computed analytically for these Debouchet wavelets. So turns out they're rational numbers that depend upon the Debouchet index, capital K. But you can calculate them. The other field theory we'll look at is the scalar bosonic free field theory with periodic boundaries. So this has a field operator capital phi and a conjugate momentum capital pi. And the critical parameter here is the mass, again, m0. So these fields satisfy the canonical commutation relations for bosonic fields and conjugate momenta. And in the massless phase, the correlations for the phi-phi correlations are algebraic decaying, as are the pi-pi correlations. Whereas in the massive phase, these correlations fall off exponentially with a correlation length that's determined by the mass. And so again, for this Hamiltonian, you can discretize using scale fields, so that we just replace the field operator phi with a mode associated to scale field at scale n and position L. and same thing for the pi's. And then we're just going to have a coupling matrix, which will couple the fields at different positions. So, and what I described now, we're mainly going to be concerned about how we can take this description I just gave, where we're really describing the field theory on these red degrees of freedom. So it's like remember the red degrees of freedom are the scale degrees of freedom at some chosen scale, however small, fine-grained you want to get. That depends on maybe your computational capabilities. And we're going to try to understand how these look like at coarser scales. And so that'll involve things like trying to work out correlations between 2 degrees of freedom, which are separated by position J, but are at both the same scale R, which is coarser than your initial scale. And this is the kind of thing you get out. So here's an example of what the coupling matrix, which describes the coupling between the degrees of freedom, as well as the ground state covariance matrix looks like for the bosonic field theory. So on the top, I'm illustrating what the Hamiltonian that describes the coupling between the modes looks like. And on the bottom, so the top looks at the case where we just focus on this boundary theory. So the top 2 panels refer to just describing things in terms of the red modes at a fixed scale. So the Hamiltonian is nearly diagonal. If you zoomed in there, you'd see some small off-diagonal elements corresponding to the derivative coupling between the different close scale modes. And the covariance matrix for the phi-phi correlations looks like this panel on the upper right. Instead, if you go to the multi-scale picture, so that's describing things in terms of these blue dots, these are the wavelet degrees of freedom. Now your coupling matrix does, as you suggested, does have coupling across scales. And that's described by this kind of finger pattern. So there's this dominant coupling that's nearly diagonal, which is within the same scale, but then you see these finger patterns which represent couplings across scales. So like this first finger away from the diagonal tells you how the coupling goes from scale n to scale n-1, and then to scale n-2, etc. And you actually have coupling across all your scales. And when you look at the covariance matrix in this multi-scale picture, you get this kind of result which looks reminiscent of what we saw with the wavelet transform of the photo earlier of the Sydney skyline. This is, in fact, you could view this as a JPEG representation of the covariance matrix. So like if I were to just take the upper left diagonal square patch of that covariance matrix, that would be a compressed version of this upper block covariance matrix in the top right panel. So using the multi-scale representation of the ground state of let's first look at the fermionic case. So this is the Ising model quantum field theory. We can calculate the correlations between the Majorana field operators at some scale R. This is something that's coarser than the initial boundary scale we had, and some separation L, script L. And what you find is in the critical phase, not surprisingly, the correlations fall off algebraically. But now this algebraic decay depends upon the choice of the wavelet family I use. So here I've plotted these correlations for lots of different choices of the wavelet family, from capital K is 3 to capital K is 7. And you see that if you choose larger index K, the correlations fall off faster. And actually you can show that, get an analytic expression for what these decays look like. The polynomial decay with an exponent that's linear in the index K. These other terms refer to moments of wavelets which can be computed recursively. And in the massive phase, then we have correlations which fall off exponentially with separation. And here what's notable is that the decay rate actually is described by a correlation length given by inverse mass, but where this mass is a renormalized mass. So there is some base mass at my boundary. And if I look at wavelet transforms which go coarser and coarser, it's like I increase the effective mass of the theory by a factor of 2 for every coarse graining. And that's very well captured in terms of the correlations here. And there's a very simple way to understand that. Oh, sorry. Yeah.
Can you see this in this picture that you drew, that this mass?
Yeah. So what I've plotted here is the correlations as a function of separation for different bulk radii. So the bulk radii here refer to how far out you out, where large radii corresponds to getting finer scale, and smaller radii means more coarse. So if we look at this, when the radius is very small, like 0, then these correlations fall off extremely fast. And then if the radius is bigger, the correlations, they're falling off exponentially, but with an exponent that's smaller. So the exponent actually goes like this renormalized mass.
So here you have a very simple relation between m0 and m tilde, which is simply a power 2 to the power n minus r. Is there any reason for this, that simple here?
Yeah, so that's right. So if we go back to the Hamiltonian, so I was looking at the fermionic one. If you were to rewrite this Hamiltonian in terms of coarser grained fields, then you get a factor of 2 from the derivative operator, whereas you don't get any factor on the mass term. So as you go coarser, it's like the relative effect of the mass term increases by a factor of 2 relative to the derivative term. And if you went to extremely coarse, the mass term dominates. And the ground state is one that tries to minimize the energy for the mass. And so it tends to want to have extremely short-range correlations, or in the limit of infinite mass, there's no correlations at all.
So it is a consequence of being a free theory, essentially.
Yeah.
Thanks.
Sure. And the same thing happens with the bosonic one. If you look at this Hamiltonian for coarser modes, then you get a factor of 2 difference between the term involving the derivative term and then the mass term. And if there is a finite mass m0, then if you go coarse enough, this mass term totally dominates. And so the minimal energy will be one that minimizes the variance of the field at every mode. So it looks like a squeeze state where it's highly squeezed in position or mode space phi, and the correlations go to 0. So this study of the correlations can also give us some information about entanglement structure within the ground state of these field theories. And a very particularly useful measure of entanglement is the mutual information. So it tells you about correlations between two regions of space in a basis-independent way. So when you just look at the correlations like the phi-phi correlations or pi-pi correlations, that's choosing a particular basis. But if you want to just be blind to basis, then the mutual information is a suitable quantity to do that. And the mutual information between two regions A and B is the sum of the von Neumann entropies for the reduced state on regions A and B minus the entropy of the state with support on both A and B. And what we find is that in the critical phase for this Ising model field theory, then the mutual information has a closed form expression which falls off algebraically with the separation of the fields at some fixed scale R. And similarly, for the bosonic theory, you also get algebraic decay of this mutual information. So there's a connection to the mutual information and the geometry of the space that describes these bulk degrees of freedom. So this is a way to see an aspect of holographic duality, where if we make the ansatz, and this ansatz was first made by Chi in 2013. So he suggested, let's just say that this mutual information between 2 points falls off exponentially with the geodesic distance between those 2 points in some space. And if we're in a critical phase, so that we have algebraic decay correlations, then that's consistent with a geodesic distance for a negatively curved space, where you would have the distance between 2 points at some scale R and separation J is proportional to the log of J divided by the radius of curvature of your space. So just to give you a little picture here, like here's 2 degrees of freedom at some scale R and separation J. And so in the critical phase, the shortest path between these two is given by this geodesic, where I've illustrated it here as if it were a negatively curved space. And then when you do that, from these derived quantities we have for the fall off of correlations using the wavelet description, you can actually derive what the radius of curvature of this negatively curved space looks like. So here we found expressions for radius of curvature for the bosonic critical phase, conformal field theory, and also for the Ising model CFT. And both of these radii curvature depend upon the the Derbyshire index that determines the wavelet family. But notably, the radius of curvature is smaller for the Ising CFT, but they both grow linearly with the Derbyshire index K.
Sorry, can I ask? So this answers about some information geometry. There will be some. It will be the for exponential with the distance, geodesic distance between these 2 points. How general this is? Is it? I mean, is it? What was the motivation for the original proposal? Was it proposed very generally, or it was just?
Yeah, it was proposed to make a connection to ADS CFT. So it's not the most general form, no, certainly not. And you know, it's a well-motivated conjecture for conformal field theories. And you can also do the same thing if it's just a regular non-critical field theory. It's just then your geodesic distance, instead of having this logarithmic scaling, will just be linear in J. So it works for those 2 kinds of phases. But it's not general in the sense that you could certainly imagine other kinds of states which have a very different kind of entanglement pattern, which wouldn't satisfy this.
So if suppose we have not the vacuum, but say, or the ground state, sorry, not generally the ground state, but some other kind of some slightly excited state or something. It's also typically if one might may expect there's also some geometry associated, but it's not. I mean, it may not have constant. It may have constant radial curvature R, but not necessarily the Ricci tensor need not be uniform, or it may not be a complete. You can break the isometries in somewhere inside. So, is there some check on this, or one can check if that this goes on not only for the ground state but also some other states? One can associate some geometry. The purpose is that one could try to understand what kind of geometries these states give rise to, and so is there some study on?
Yeah, absolutely. Those are excellent questions. In fact, my student is starting to look at that for excited states. But you're absolutely right. Then you shouldn't expect there to be this kind of constant radius of curvature. There is some work on what this looks like for a thermal CFT, and that was looked at by Chi for one kind of wavelet, where he showed that it, in the case of a 1+1 dimensional CFT, particularly the free fermion model, that the thermal state on the boundary has a bulk entanglement pattern which mimics features of a BTZ black hole. So what you get is like you've got this boundary theory which is thermal, so it's got some entropy, and then when you do the wavelet transformation, what it does is it kind of compresses the entropy into the very coarse modes, which kind of mimics some features of black hole.
I see.
But no, this issue you raise about what happens if you look at particular energy eigenstates is an interesting one.
I see. Okay.
So something we looked at as an application for this wavelet picture is to study holographic subsystem entropy. And here I'll just look at it for the case of the bosonic CFT. So it's well known that the subsystem entanglement entropy of a bosonic 1+1D CFT is equal to the length and actually this is not just for bosonic, but for any 1+1 CFT, is equal to the length of the geodesic joining the boundary points in the bulk geometry, which is negatively curved. So like here, if I had a 1+1 CFT where I just look at a time slice and I impose periodic boundaries, and we have a subsystem A, then the entanglement of this subsystem A would be proportional to the length of the geodesic in a negatively curved space that connects the boundary points of A. There's a prefactor C/3 where C is the central charge of the theory, and then epsilon here is some cutoff for your description of the theory, some spatial cutoff, or well, it's a momentum cutoff which gives you a minimum spatial resolution. So this was formalized in the paper by Ryu Tagenaki. And if we had two regions like A and B, then if these regions are very far apart, then the entropy of the joint state of rho AB would just be the sum of the entropies of each, which would just be the sum of these two geodesics. And if they're the same size regions, then it would just be twice that size. But if we look at the mutual information between two subregions A and B, then you get some interesting behavior depending upon the size of these regions relative to the size of the entire system. So when the separation between the two regions, which I call little d, is very large relative to the size of each region, which I call little l, then the mutual information is 0. And that's basically just because the minimal length geodesic that couples the boundary points of the joint system is just equal to the sums of the minimal geodesics for the individual systems. But when the distance between the two regions, little d over little l, becomes small enough, then actually the minimal geodesic connecting the boundary points of the joint region is given as this lower figure here. And in that case, your mutual information becomes greater than 0. And so you can view this as a phase transition of the mutual information that depends upon separation between these two regions, A and B. And there was an attempt to better understand this made by Tagenaki some years ago, back in 2017, where he considered a geometric quantity, which is something called the entanglement wedge for a subsystem rho AB. That's illustrated here on the right. You've got some system, so it's CFT on the boundary, and I've got a region A here on the left and a region B here on the right. And this entanglement wedge is illustrated by this gray region. And this quantity EW is defined to be the length of the minimal surface which cuts across this wedge divided by some constants. And in the case that the system is a conformal field theory, you can geometrically compute what this minimal surface cut is, given by this equation C/6 log 1 + 2L over D. And so Tagenaki conjectured that there is an equality between this geometric quantity EW and the entanglement of purification of the state rho AB. And this conjecture was motivated by some inequalities that are satisfied by the mutual information and the entanglement of purification. And it's the entanglement wedge. So a way to view this in a wavelet picture, this is something we decided to look at, is the following. So if we consider the mutual information between two regions A and B, then, at some boundary scale n, you've got all these black degrees of freedom, and there are these two regions A and B. And if it's a critical phase, then the entropy of rho A will have this be determined by the length of its geodesic connecting the boundary points, and the same for B. And I've shown the multi-scale representation here. So the blue dots are like one wavelet transformation applied, which coarse grains, and then successive blue dots are further coarse graining. So in the upper picture, the mutual information is 0 for rho AB. But if you make the separation between these two regions A and B smaller, so you make D smaller, then you start to get an overlap, which can actually be seen in terms of these bulk modes, these wavelet modes. So this minimal cross-section that cuts the entanglement wedge actually can be understood in terms of like degrees of freedom in the bulk description that are traversed. So this would have a mutual information greater than 0. And so we wanted to see whether we could use the wavelet description to actually compute this entanglement of purification to test the conjecture. So the entanglement of purification for a system rho AB has the definition that it is the minimal entanglement for a purification of the state rho AB across two subsystems. So what you do is you imagine you got your subsystem A and subsystem B, and you have some state with support on those two. And what you do is you want to purify that state rho AB by attaching some ancillary system A prime and ancillary system B prime. And then you look, so there's a pure state across all four systems. And then you look at the reduced entropy of just rho A prime, and the minimum over all such purifications gives you the entanglement of purification between rho AB. So that's how this quantity is defined, and it generalizes entanglement entropy for mixed states for both classical and quantum systems. But unsurprisingly, this is a very difficult quantity to compute because you're asking to do a minimization over these pure state purifications, which can involve many degrees of freedom if your subsystems have many degrees of freedom. So it becomes extremely onerous to compute. And in the paper by Umemoto and Taganaki, they were only able to compute it for cases where the systems A and B only had a very few modes. But what we realized is that we could do it using wavelets by basically performing a compression on the regions A and B. So you would only represent regions A and B by a very few degrees of freedom. Namely, like here, just in this lower figure here, maybe you just represent it in terms of the most coarse degrees of freedom and maybe the next most coarse degrees of freedom. So we looked at that and treated the state as if it was represented well by those coarse degrees of freedom. And then we're able to perform the minimization over the purifications and looked at what the covariance matrix looked like for these compressed states as a function of this parameter d over L, which, if you recall, determined whether it was going to be phase transition. And in fact, you do see that there is an indication of a phase transition near where d over L is equal to 2. So at least we were able to find results that are consistent with there being this phase transition in the entanglement of purification, which is a nice thing because we were able to do it with not a very difficult calculation, just making use of this compressed representation of the theory. And one other thing we looked at is how we could witness phase transition in terms of fidelity overlap. So one measure of a phase transition is to see a dramatic change in the fidelity overlap of ground states. And this is defined as the overlap where you take the ground state of the Hamiltonian at some parameter g plus with the ground state with the Hamiltonian having parameter g minus. And if you cross a phase transition, these two ground states will have dramatically different correlation structures. And so you see a dramatic reduction in this overlap fidelity. Now, typically this overlap fidelity can be difficult to compute if you have a multipartite system, and you have to keep track of all the degrees of freedom. But our approach was to try a compression again and reduce the description of the state to just a very few coarse modes. And then you can look at the fidelity overlap with respect to the reduced states on those very few coarse modes. So there's a mixed state expression for the fidelity overlap given by this expression. And we wanted to see whether this would be observable. So here's what the results look like for the Ising model field theory. And what we're looking at here is the fidelity overlap of a few coarse modes as a function of the mass parameter that shows up in the Hamiltonian. So when the mass goes to 0, there's a phase transition. And so we should see a dip in the fidelity when the mass goes to 0. And the gray dotted line is what you get from the full fidelity overlap of the full state. Whereas these other lines are what you get when you look at just the fidelity overlap of a pair of modes, but with different amounts of compression. So more compression gives you a more prominent dip. And that's consistent with the fact that the more compression you do, the better representation you get of the state over a very small number of modes. So this could be useful in experiments if you wanted to, for example, let's say in a lab, you prepare an approximation to a quantum field theory state, and you want to do a measurement of fidelity overlap. Well, it can be very difficult to do this full overlap measurement, but if you can perform the compression, then you would just have to do tomography on a very small number of modes, and you'd be able to infer the phase transition. So I know I'm getting kind of late here on time. Maybe I'll just, maybe I should just, maybe I'll just skip the part on engineering these phases and just close with, we've been also looking at how one could use the wavelet description in quantum algorithms for simulating quantum field theory. So there have been many proposed algorithms for simulating quantum field theory, including lattice gauge theory. And we were particularly motivated by the proposal by Jordan Lee and Preskel for a quantum algorithmic simulation of interacting bosonic field theory. And here the general idea is that you could take, it could be a one-dimensional, or it could be a higher dimensional field theory, which you discretize, and then you encode the field into some qubits. So at every point in space, you're going to have many qubits which represent the field amplitude at that point in space. And what we looked at is, what if you do this using a wavelet encoding? And it turns out that you can find an efficient algorithm to prepare the ground state of the scalar bosonic free field theory into a number of qubits with a complexity of the algorithm scaling like v log v, where v is the number of modes in your description of the system. And this is asymptotically optimal in the sense that there's a lower bound on the time cost, which is order v. And so this is described in this paper, PRX Quantum, from this year. And we show that the wavelet encoding has some benefits over, say, a naive lattice encoding, in the sense that you can faithfully represent the ground states of systems where you have some broken translational invariance. So maybe you have like a mass defect. Then the multi-scale encoding with wavelets gives you an efficient representation of that ground state, and you can do it. You can encode it efficiently with a circuit. And then you can prepare excitations in the wavelet degrees of freedom and give them a momentum you like. Adiabatically turn on your interactions, the quartic interactions, and then study particle physics. You can measure scattering matrix elements. And importantly, in the wavelet construction, you can study the correlations or scattering between particles at different scales natively, without having to do a complicated transformation on your basis set. So yeah, I'll just conclude with that wavelet basis is kind of a natural one to study holographic duality in field theory, and it gives you access to observables at multiple scales, and it gives you an efficient way to compute quantities which could depend on different scales, with features that might not be easy to access if you're using a fixed scale basis. Okay, so that's it.
Thanks a lot for this great talk. So we have time for questions, and take questions now. Questions?
I have one.
Yeah.
So in the beginning, when you defined the wavelet basis, there were some coefficients, some weights that you used to define the.
Yeah.
I didn't see that they played.
Is these HJs?
Yes, it's H.
Yeah. So were you wondering how those are calculated?
Are they calculated, or I thought I understood that how you define the basis. So it's something you calculate. It's not something you input.
Yeah, so for this family of Derbyshire wavelets, those coefficients are calculated, and they're determined by demanding that the wavelets are compact and that they have a vanishing set of moments. So the first k moments of the wavelet functions vanish. So from those conditions, as well as orthonormality conditions, you can work out what these HJs are. But you know, this is only one family of wavelets, and you might ask, well, maybe I should pick my wavelet family according to the quantum field theory I want to study. And you know, you might want to think of it very similar to how we view tensor networks, where when you want to describe, you know, sort of the renormalization fixed points of a phase, you could think of a tensor network as one step of renormalization corresponding to gates where you remove short range entanglement and pass on longer range entanglement. And actually, that kind of circuit looks like a wavelet transformation. It looks like a transformation where it's an isometry where you pass on coarse degrees of freedom, which in this case would be like scale degrees of freedom, and you leave behind the fine degrees of freedom, which would be like the wavelet degrees of freedom. And so, you know, in tensor networks, your choice of the disentangler depends upon the state, and if it's a ground state, then it depends on the Hamiltonian. So you might ask, well, could I pick some of these coefficients so that I sort of ideally remove short range degrees of freedom? And in fact, you can do that. The cost is that you have to use a different basis set for every Hamiltonian, but it is possible to do. So, for example, Michael Walter has done this and for scalar bosonic field theory, and it's also been looked at by Glenn Evenbly and Steve White for the case of a free fermion theory. But then, as I was pointing out, you have to adjust things. You don't get a uniform basis for every renormalization step.
Yeah, I remember seeing this Evenbly white paper that is where they're doing sort of mirror-like. And so I wanted to also ask in a similar vein that the fact that you're getting this geometry out in the context of this entanglement entropy, oh, sorry, the mutual information, sorry, the mutual information. So
yeah.
This does depend so much on the choice of basis or not? I mean, is it the K that you got, the radius of curvature? Suppose
Yeah,
I choose
so
the basis, will it change a lot or?
So yeah, it's you're going to get this feature of having a radius of curvature, but I think we were the first ones to look at how this radius of curvature changes with the wavelet family you use. So, and it has a very natural description, actually. You can think of the radius of curvature as telling you some information about how fast you renormalize a state. So larger K corresponds to using these wavelet families that are smoother, that have more vanishing moments, that give you better approximations to functions. So in a sense, they renormalize a state faster. And that shows up in the radius of curvature. It's like telling you how fast you renormalize.
See. So there could be some optimal choice of, if there is some kind of optimal choice of wavelets for a certain Hamiltonian, as you were saying, or for certain theory or state, how do you see it in this language? I mean, is there a way to?
Well, yeah. So the thing is though, if you use a different, if you use an optimal one, the choice of your basis will change depending on what radius you're at. So that's part of the reason why we stuck to a fixed basis, because it gives you a uniform radius of curvature throughout. Yeah, so I don't really have a good geometric picture if the basis changes with the radius.
So
I'm not sure there is one.
In holography, you won't expect the radius to change with the non-uniformly, with not with the scale. If you are dealing with a CFT,
Yeah.
And but if there is some kind of RG, it's okay to run. I mean, this probably captures some good information after all.
Yeah. Yeah, that's right. Yeah, I mean, I don't know. I guess it depends on kind of what you want to do with it. If the goal is to make a contact with holographic duality, then it maybe is easier to work with a fixed basis. But if your goal is for computational efficiency to understand the physics of the fixed point, then it would be more efficient to work with an adaptable one.
Actually, I was saying the opposite, that if you want to make contact with holography, maybe the choice of wavelet should be more precise in a way, because
oh, I see what you're saying.
There should be a principle that chooses the wavelet basis.
Yeah, I guess, but then I'm not sure though, because the radius of curvature, or sorry, the geometry, the radius of curvature actually is determined by the central charge, right? But you can have very different entanglement structures with the same central charge. Or, you could, have very different states with the same central charge.
Yes, but this is something, a simple correspondence between the central charge and the radius of curvature. That is something that one can always take as part of the choice of the basis. But more when you put an excited state, if you have to see something like local equations come out, local gravitational equations come out, when they do come out, then probably there is some optimal choice of basis that should work to see something like local gravity come out, where you have only locality in scale, as much locality in scale as possible.
Oh, I see. Okay, so you're thinking of looking at the excitations.
Excitations, and probably you want to keep the interactions as local in scale as possible. So in that sense, if you want to get something like local gravity out in some limit, then there should be a way to choose a good basis.
I see. Yes.
Yeah. Just the one, you will not get gravity in the bottom.
Yes, but I said probably there is some principle of that reduces to good, gives gravity in the right regime.
Yeah, that would be good to look at. Actually, most recently, we've just started to try to understand how wavelets fit into a band limited formulation of quantum field theory. So There, it's more convenient to work with continuous wavelets as opposed to these discrete wavelets, where we have a discrete index for the scale and position. The continuous ones have a continuous scale index. And so we're looking at trying to understand things like Sakharov's induced gravity, but in a wavelet basis. But that's the most recent stuff. So not really holography, but just trying to understand the effect of band limitation from a wavelet perspective.
Thanks. So yeah, it was thanks for the talk again. So
Sure.
I stopped the recording, but we can have a little small chat after that.